This video goes over the properties of polynomial functions in order to help you graph them. And so to graph p at x, you need to know a couple of things. The very first one is the zeros, and these are also known as the x-intercepts of the graph. The first thing that you're going to do is set your function equal to 0, and this is called your related equation. And in order to solve that equation, you are going to use the factor theorem, long divide, factor, quadratic formula. Some of those things you've seen before. Other things we're going to take a look at later in the unit. So the solutions to your related polynomial equation are the zeros, or the points that are on the x-axis. So if I draw a sketch here, some polynomial function, the solutions to that p at x equals 0 would be my 3 x-intercepts. Those are the zeros. And so that's important to know because you need to know where the function crosses the x-axis. The next thing that you're going to consider is the degree. So whether it's odd or even. So odd polynomial functions have exponents that are odd. So this is an example of an odd degree polynomial. This one is also an example of an odd degree polynomial. The highest exponent in there determines the degree of the function. If that highest exponent is odd, that makes it an odd degree polynomial. Even would be if your highest exponent is even, and in expanded form it looks like this. My highest degree exponent is 6. That 6 is even, so that means that my function is an even polynomial. Once I've figured out the zeros, I've figured out the degree. Next, I'm going to check out the sign of the leading coefficient. So if the leading coefficient is positive, that could look like this. It could look like this. Or it could look like this. We'll write one out. This one is also the leading coefficient positive. And the leading coefficient is going to give you a clue in combined with the degree to tell you what the end behaviors are. So a negative leading coefficient would look like this. So it might have a negative sign at the front, or the first term might be negative if it's written out in expanded form. So those two things are going to help you to determine the end behavior along with, there we go, the end behaviors. So if you have an odd degree polynomial, let's underline in red, and a positive leading coefficient, then your end behaviors are going to look like this. So it's going to finish to the right and looks like it's coming from the left. Okay, or we can write as x goes to infinity, y goes to infinity, and as x goes to negative infinity, y goes to negative infinity. So that just means that as x gets really, really big, so does y, or as x gets really, really big negatively, y also does. So let's see, if we have an odd negative, then we've got the opposite situation. So we've got our little grid here. If it's odd negative, that's the same as a line with a negative slope. It is falling to the right. And so that means as x goes to positive infinity, y goes to negative infinity. And as x goes to negative infinity, y goes to positive infinity. The other two situations that we have are even positive. And so that's like the upward facing parabola. They both point in the same direction. As x gets bigger, goes to infinity, y also goes to infinity. And then as x gets bigger negatively, y also goes to positive infinity. Even negative, we know that they're going to finish in the same direction. And if the leading coefficient is negative, then they finish down. And then we can summarize the behaviors like this. So as x goes to infinity, y goes to negative infinity. And as x goes to negative infinity, so does y. The other thing that you need is to figure out the turning point, which tells you about the middle part of the graph, how many times your graph changes direction. If you have a first degree function that is linear and it has 0 turning points as a maximum. Second degree function is quadratic and you have at most 1 turning point. Cubic is degree 3 and you've got at most 2 turning points. 4 is quartic and you have at most 3 turning points. N is our nth degree function or polynomial, and our maximum number of turning points is n minus 1. So that tells you about the middle part of the graph. Our next feature is the zeros, and this is also known as the multiplicity of roots. And the exponent that goes with the root tells you how they behave around the x-axis. So if you have a 0 of order 1, that just means at that 0, the graph crosses the x-axis. If you have a 0 of order 2, that just means that the graph behaves like a parabola around that root. If you have a 0 of order 3, then the graph crosses but behaves like a cubic around that root. Order 4, we'll keep using x minus 3. Looks more like a quartic function, kind of like a parabola. And then order 5 is slightly more squiggly than a cubic, but still goes through the x-axis. So all of the odd degree roots, 1, 3, and 5, the function goes through the x-axis. All the even roots, the function just touches the x-axis. So we want to apply that to some situations. So here we're going to determine the end behavior of the following functions. So to determine the end behavior, we need to know the leading coefficient and we need to know the degree. So our leading coefficient here is negative and our degree is 3. So that means that we've got an odd polynomial. So our function is finishing in opposite directions and it is negative. So I'll write it both ways here. We've got the little graph to represent what is happening as x goes to negative infinity, y is going to go to positive infinity. In our second example, our leading coefficient is positive. We've got 0.5 and our degree is 4, which is even. So that means that to draw our little sketch, both ends are finishing up. They're going in the same direction, or x is going to get larger and y. And then as x goes to negative infinity or the other direction, y is still going to be getting larger. So the last couple examples, we are going to determine the zeros, the y-intercept, the end behaviors, sign of the leading coefficient, and then the turning behaviors of the functions. So we'll start with these zeros. They're all in factored form, so those are pretty easy to pick out. Those are just like you're finding the vertex or the zeros of a quadratic, The zeros are just the opposite of whatever is in those brackets. So let's go through, we'll do those for all 4. So we've got -2, -5, and 4. Really what I'm doing is setting each bracket equal to 0 and then solving. Shortcut is just taking the opposite sign. Zeros, 5, and -1. So the next thing that I need is the y-intercept. So I'm setting x equal to 0. And I'm going to calculate that. So for here, I'm going to get x is 0, y is -3. If x is 0 here, I'm going to end up with 40. I've got 2 times 5 is 10, times -4 is -40, and then there's another negative sign. My y-intercept here, again, I'm setting x equal to 0. I'm going to get 32 when I evaluate that. And for the last one, I'm going to set x equal to 0 and evaluate. So that means I have -5 times 1, which is -5, and then times 3 would give me +15. So we've done the zeros, the y-intercept. Now we're going to do the end behaviors. Okay. Let's actually we'll do our leading coefficient first, because that will help. So our leading coefficient in A is positive. Leading coefficient in B is negative. C is positive. And then D is negative. For our end behaviors, we can draw our sketch. So my leading coefficient is positive, and my degree is 2, because I've got 2 x's here. So that means that my function is opening up. Oops. And then my end behaviors for the next one, my leading coefficient is negative. My degree is 3, because I've got 1, 2, 3 x's here. And so my end behaviors are negative, odd. So I'm going down and to the right. For C, I've got a positive leading coefficient, and I've actually got a 3rd degree polynomial, because I've got 2 x's in that second bracket and then 1 in the first. So then I'm finishing up to the right. And the last one, I've got 3 x's from that last bracket and then 4. So I actually have a degree 4 polynomial, and it's negative. So that means I've got even negative, so it's opening down. So the last thing that I need to figure out is the turning behaviors. I'll use TB for that. In my first one, I know I've got a parabola. I only have one turning point here, based on the fact that both of my zeros go through the x-axis, and I have to get back up. I can fill it in on my little sketch here. In my second one, I've got a cubic, so at most I can have 2 turning points. And I do in this case, because I'm actually going to have 3 distinct zeros. And when I kind of fill those in on my end behavior sketch here, if I cross the x-axis 3 times, I'm going to end up changing direction twice. Down here for C, I've got zeros at -2 and +4. Now the one at +4 is a double root, so that means that my sketch crosses through at -2 and then touches and then goes back up. So I still have 2 turning points here. I've still changed direction twice, even though I didn't go through the x-axis on the second one. And the very last example here, I've got degree 4 one of my roots is multiplicity 3. So let's see, on the right, my fifth root has multiplicity 1. So I'm going to go through the x-axis. And then in my second root, I'm going to come through the x-axis, but it's going to be more like a cubic. So I really only have 2 turning points here. And that's a summary of the properties of polynomial functions.